Okay, today we're going to see classification methods. The reference we're going to use for this chapter are the book for the class, as well as the excellent reference and the really complete Rasmussen and Williams Gaussian process for machine learning. And there's also an excellent tutorial, Gaussian process for classification, a quick introduction by Ebden. So what is classification? What we saw with regression is what we were trying to learn, the relationship between covariates and system response, where both the covariates and the system response were continuous quantities. Okay, in this case, we're going to try to do a similar task where the covariates are continuous quantities, yet the system responses are going to be classes. Here's an example. We have the presence or absence of pathogens as a function of chlorine concentration. Okay, each of the dots here represents an observation of a given class. So for the low value of chlorine concentration, we see we have several observations where there were pathogens. For higher chlorine concentration, we see many observations where there are no pathogens present. Okay, so for super high chlorine concentration, we see we haven't seen any cases where there were pathogens. On the opposite, for low chlorine concentration, we have no observation where there were no pathogens present. Okay, so here +1 represent the observation where there are pathogens, and -1 the observation where there are no pathogens. So with classification, what we're trying to do is to retrieve the following function: the probability of having pathogens given the chlorine concentration. It would look somehow like this red line, where for low chlorine concentration, I have a super high probability, so something close to 1, of having pathogens. And for high chlorine concentration, I have a low probability of observing pathogens. And in between, where both is possible, the probability is going to be in the vicinity of 0.5. So in that context, my data set D consists in D tuple of continuous covariate Xi and Yi and observed system response, where Xi, my covariate, is, as before, a continuous quantity, and Yi, my observation, is going to be a discrete class, either -1 or +1 in this example, if we're looking at binary classification. So we're going to see most of the methods that we're going to see this week in the context of binary classification, but keep in mind that we can extend this easily to multi-class classification. So not only 2 possibilities, and possibility, or an arbitrary number of possibilities. So the bottom line of this, another example here, if we have another context of application of classification, we want to classify the probability of damage in buildings following an earthquake given the peak ground acceleration that is a proxy for the intensity of the earthquake. So we see that for high peak ground acceleration, so high earthquake intensity, the probability of damage is much higher because we have many observations of damaged building. On the opposite, for low peak ground acceleration, the probability of damage is fairly low, and what we want is to reconstruct that quantity. So as we said before, machine learning is not necessarily there to retrieve quantities like they're in one dimension. Okay, what we want to see is how does it work with one dimension, because we can really see what's going on. So then we can extend this to multiple class, multiple attributes. Okay, but the bottom line remains the same. What we want to do now with classification is to develop mathematical model for modeling this conditional probability. The probability of Y, which is here a class, given X, some covariates. So there are 2 main types of classification methods, classification approach. So the first one is what we call generative approach. So what we want to have is to model that conditional probability of a class based on the Bayes rule, okay? So what we're going to do is that we're going to characterize what is the conditional probability of my covariate given a class times my prior probability of a class divided by my marginal probability for the observed covariate. Okay, this is generative because here we're going to model the joint PDF by this product here on the numerator of my observed covariate and observed class. Okay, that's going to offer me, we're going to see it, some flexibility. The other approach is what we call a discriminative approach. Okay, so what we'll want to do is to build ourselves a kind of generic function that I represent here by g of x. So that generic function takes as input my covariates x. And what we want to do is to use that generic function in order to model directly that conditional probability without necessarily going by this Bayes rule where we model the joint for y and x. So here's for the introduction, the outline of the course today. So we've already looked at introduction. We're going to first introduce the concept of generative classifiers. And we're going to look at what are the special case, naive Bayes, linear discriminant analysis, quadratic discriminant analysis. Then we're going to look at the first discriminative approach. In this case, it's going to be Gaussian process classification, GPC. It's just a natural extension of GPR, Gaussian process regression. Then we're going to move to neural networks that are going to be used as another discriminative approach. So we are here. So we've already seen regression. So classification is going to be an extension of those regression methods. So let's start with generative classifiers. Okay, we're going to see a brief introduction. What is the mathematical formulation that is common to all approaches? How can we extend that formulation that we're going to see for 1D cases to multiple cases? And how can we apply this to some examples? And then we're going to see an example, a real-life example with real data. Then we're going to see what are the classical generative methodology, namely naive Bayes, linear discriminant analysis, quadratic discriminant analysis. And then we're going to see what are the strength of limitation of such a generative approach. Okay, so as a reminder, what we want to obtain at the end is the curve represented in the red here that describe the conditional probability of a class, in this case, the presence or absence of pathogens, given my covariates, in this case, concentration in chlorine, okay? And to do this with generative classifier, what we want to do is to model the joint, okay? The joint between y and x, meaning here the class and the covariate. So this joint can be expressed in two ways, either by the conditional probability of a class given the covariate times the PDF for describing the density of the covariate. So here, notice and remember, P is a probability mass function because Y here is a discrete class, and F is a PDF because X is a continuous quantity. But we have two ways to describe this joint PDF. Either through the conditional of y given x times f of x, or through f of x given y. So the conditional PDF of my covariate x given my class y times my prior probability of the class y. Okay? Then I think you see where I want to go. If we reorganize these terms, we're going to get through Bayes' rule. That's going to explicitly describe such conditional probability. So the conditional probability of y given x, this is what I'm looking for here, is going to be modeled by here my conditional probability density function of my covariate associated with a given class y times the probability of that, or the prior probability of that class y, divided by f of x, which acts here as a normalization constant. Okay, so here we can reframe this as we're trying to quantify what is the probability that my random variable y takes the class I given a covariate value x. Okay, so this is the conditional PDF for my covariate x given that the class is I. So here what it would represent, this term here, would be the PDF, say, for a given class. That class could be the class -1, no pathogen, times what is the prior probability of having no pathogens with respect to the prior probability of having pathogens, divided by f of x, which is going to be my normalization constant. Okay, normalization constant, what is it going to be? It's going to be the sum of what I could have on my numerator for j, my possible classes. In this case, it would be the PDF of the class minus 1 times the probability of that class plus the probability, the marginal probability of having pathogens times the probability of having pathogens, okay? And I do the sum, that's going to be my normalization constant. So let's look in more detail in that formulation for binary classification. So here again, it means that my observation y could either be minus 1 or plus 1, okay? I have only two possible outputs. Minus 1 represent one class, plus 1 represent the other class. And what I want to do is to quantify this posterior through the likelihood, the prior, and the normalization constant. So the posterior probability of a class here really describe, this is a probability mass function. Since it's binary, it's made of two things. Either the probability that y equal minus 1 given x, or probability that y equal plus 1 given x. And here, since I have only two classes, I know that if I characterize one, I can obtain the other by the complement, one minus the other, okay? So as represented here, I can obtain the probability that y equal plus 1 by 1 minus the probability of y equal minus 1 through the complement rule. Then P of y is going to be my prior probability, okay? In general, what is the probability of having no pathogens versus what's the probability of having pathogens, okay? Some cases it can be 50-50, some cases it can be widely imbalanced, okay? The likelihood, what is it? These represent some probability density function, okay? This represents the probability density function for class minus 1. This represents the probability density function for class plus 1, okay? So here what we have is two probability density function, one for the class y equal minus 1, a second one for the class y equal plus 1, okay? So this here is really a conditional PDF. So when y equal minus 1, I have a PDF. When y equal plus 1, I have another different PDF, okay? And here, what differ between these two PDF, it's actually its parameter values. So the normalization constant, f of x, what is it? It's actually the normalization of the possibilities I have on my numerator. So f of x is going to be the sum over y, maybe equal to minus 1 and plus 1, of my likelihood times my prior probability of a class, okay? I do this summation for my two possible observations. And here, keep in mind, this is a normalization constant, so at the end you're going to obtain a single digit, a single number for this quantity. So the key here is, how do we learn the parameters for all the quantity we have in that generative classifier, okay? So we need to learn the parameters associated with either the PDF here in the likelihood or the PMF in my prior, okay? And we need to learn these parameters through my data, through my observations of classes associated with covariate responses. And the way to do this is the same way as we saw before. We can go either through a maximum likelihood approach, which is a simplifying case that is going to be fast, but we need to satisfy some hypothesis to use it, or to go more generally with Bayes' rule, okay? That will really enable us to control the amount of uncertainty we have in our parameter estimation as a function of the number of data available. So let's first look at a special case. Let's imagine that we're going to model our conditional PDF for covariate given a given class by a normal PDF, okay? Defined for x, where x is my covariate, parameterized by its expected value, or its mean, mu, and its variance, sigma squared, okay? So if we assume that this conditional PDF for my covariate given a class, the jth class, so y equal j, is described by this normal distribution, we're going to say its optimal expected value for x given yj, and my variance for x given yj. If my data is fairly large, so I have a large D, it's going to be appropriate to use an MLE, a maximum likelihood approximation, okay? So again, when I say D is large, I should further specify as saying the number of independent data is large. So in that case, I can approximate my MLE estimate for the expected value as 1 over the number of instances where my observed class equals to J. So times the sum of the xi, the covariate value. So basically here what it means is that we're going to take the empirical average of all the covariates that belong to one specific class, okay? So this is the sum of all the covariates value belonging to a specific class divided by the number of instances for that specific class, okay? For the variance, we do actually the same thing. We calculate the empirical variance of the covariate associated with a specific class by saying the covariate value for that specific observation minus the expected value calculated previously. We're going to do this square, the sum over all my observation I, for which my observed class equals to J. And I divide by the number of instances of observed value for that specific class. Then the second thing we need to do is to use an MLE approximation for my prior probability of the class. So what we look at is what is the relative ratio of each of the class, okay? So the probability estimated using an MLE that my class Y is going to be equal to J is the number of instances of a class divided by D, the total number of observed data. Okay, by simply looking at this relative frequency of my class, I'm going to have an MLE estimate for my prior probability of observing that class. So if we put that in application, we could obtain a generative classifier such as this one. So here we have several observations for a class plus 1. These are represented by these red crosses. The observations for the other class are represented by these blue circles, okay? So what you can see here is we have here the marginal PDF here for my class in blue, the class Y equal -1. So what did I do? I calculate the expected value for that cloud point, the variance for that cloud point, and these becomes the parameters for that PDF, okay? So this is the PDF describing the marginal probability, the conditional probability of the class Y equal -1. The marginal PDF, the conditional PDF of X, so my covariate, given my class Y equal -1. I did the same thing for my second class. So I look at what is the expected value of that cloud of point, what is going to be its variance, and these becomes the parameter for this second normal conditional PDF. So conditional PDF of my covariate X given the class Y equal +1. Then if I want to do then if we want to look at my prior probability of each class, I look at how many red crosses I have divided by the total number of points. My prior probability for class Y equal -1 is the number of blue points divided by the total number of points, okay? So here, the red line represents my generative classifier, okay? It's going to be the probability that Y equal +1 given X, okay? It makes sense. When we go with higher covariate value, we have higher probability for the class 1. When we go with lower covariate probability, lower covariate value, we have lower, close to 0 probability for the class Y equal +1. And this corresponds well to the data we're seeing here. So how do we exactly obtain this red curve? We obtain it by, for instance, here we're looking at the probability that Y equal +1. So what we're going to do, we're going to look at here, what is the height of Y equal +1, okay? This height here times the prior probability of the class Y equal +1, that was obtained by the ratio of the number of red points divided by the total number of points. And I divide this by my normalization constant, which is going to be the sum of the height of a covariate value for my class y equal plus 1, so the height of my conditional PDF, times probability for that class, plus the height of the PDF for the class y equal minus 1, times the probability of y equal minus 1. I sum these two quantities, this is going to be my normalization constant. And the outcome is going to be that conditional relationship describing the probability of y equal plus 1 given x. Okay, how can we now extend this to more than one covariate? Okay, because here in that case we have only one x. What if we have multiple dimensions and we want to obtain the conditional probability? So in that case we would have x input covariance. So what we're going to do simply is to extend our model to have in the likelihood term the conditional probability density function that are multivariate. Okay, so here what we have is a multivariate conditional PDF where we look still at one class at a time, but where we model x in many dimensions. So naturally, one way we could build that joint PDF is through a multivariate normal PDF, described for my vector of random variable x and parameterized by its expected value and covariance. And we can infer these parameters, either the expected vector or the covariance matrix, using MLE or using Bayes. So for instance, here what we have two clouds of points. So we have a two-dimensional space, x1 and x2. The vertical axis here is the outcome of my generative classifier, okay? So here it describes the probability of y equal 1 given x. And what we do is that we first learn what is the joint PDF for that cloud of points. This is what we have here in red. Then we learn what is the joint PDF for the cloud of point in blue. This is what we have in blue here, okay? And then what we're doing, if we want to obtain that curved surface, is looking at what is that for a given covariate value, what is going to be the height of the red curve for that covariate times the probability of these red points. Okay, the probability, keep in mind, is going to be the ratio of the number of red crosses divided by the total number of points. So the sum of the number of red points and the number of blue circles. Okay, so to obtain the height of any of those points, you multiply the probability of the joint PDF for the class y equal 1 times the probability of class 1 divided by my normalization constant. So that same quantity plus the equivalent quantity for the other class. So the joint probability for the other class, I evaluate the same covariate value times the probability of the other class. And this is how we can obtain this thing. So if we look at it in the figure, so what you see here, so we see we have our two joint PDF. So what you can see here, I'm trying to show them to you. You have your two clouds of points. So you have a first cloud of points here. You have a second cloud of points there. Okay, the height is there just to represent which class do they belong to. So what we did here is that by looking at what is the empirical expected vector and the empirical covariance to describe the parameter of both joint distribution, where we see that they both have different parameter value. And then if we use the generative classifier approach, we're going to obtain this surface that represents for any coordinate x1 and x2, what is the probability of having a class y equal 1. Okay, so this is what we've obtained in that exercise. Perfect. So if we go a little deeper, how do we formulate multi-class classification? So in the case where we don't have only binary classification, so class y equal 1 and class y equal minus 1, but we can have multiple classes. Okay, here we're going to describe the number of classes by that typewriter face y. So the posterior probability of a class now describe a probability mass function, which is described by the marginal probability of y equal j, okay, the jth class. And I can have several of them. The probability of the class represented by, again, a PMF, probability mass function, which describes the probability that the class y equal j. The likelihood that we have here represents the likelihood of observing a given covariate x given a class y equal j. Okay, so this is for each class y equal j, this is a probability density function. And at the end, we have normalization constant, where we sum over each of the jth class the product of the joint PDF for my covariate x times the probability of a class j. Okay, let's put that in application for a real-life context. So the societal challenge we're gonna face here is right after an earthquake. Okay, there are gonna be thousands of buildings that might be potentially damaged and might be unsuited for occupation. So what we want to do is to assess quickly which building is safe, which one is not. Okay, so which one can be used as a shelter, which one should be evacuated. And we're going to look at this through an empirical study through the city center of San Francisco, which is an earthquake-prone region. So the solution to tackle this challenge of being able to make that quick assessment whether a building are safe for occupancy or not is to monitor structure. So use, for instance, an accelerometer, similar to what you have in your cell phone, in order to extract the natural frequencies of buildings, okay? And use this data-driven approach in order to assess in real time, are the building safe or not? So what we want to do is real-time data-driven learning in order to assess the safety of building, okay? This is a classification problem because here the class is gonna be the building, is it safe or unsafe, okay? As a function of a covariate, which is going to be a function of the natural frequency of our building. Outcome. Here, the covariate we're going to use here to classify between safe and unsafe building is going to be the frequency ratio. Okay? What does it represent, the frequency ratio? Is the ratio of a building after versus before an earthquake. Okay? So we imagine that the more damage a building has sustained, the lower is going to be its natural frequency. Okay, so by looking at that ratio post and pre-earthquake, we can use that as a proxy, as a useful feature to discriminate between safe and unsafe building. And actually, we have empirical evidence that show this trend. For instance, what we see on the horizontal axis is the damage index, where a damage index of 0, it means in a perfect state. A damage of 5 is collapse. Okay, and in between we have a gradation in the severity of the damage of a building after an earthquake. On the vertical axis, what we have is the frequency ratio. Okay, we see that if the frequency ratio is 1, it means that there's no change in the post and pre-earthquake frequency. Okay, so for undamaged building, we see that that correlates with very high frequency ratio. And we can see that as the damage index increases, the frequency ratio drops, okay? And that frequency ratio is going to be bounded between 0 and 1. And here are each of those points are some empirical evidence collected at some place in the world. And the points for which you see the arrow means an upper bound observation, okay? A case for which the actual frequency ratio is lower than the value that was observed here. Okay, so we have to take into account the fact as well that we might have in our data set some upper bound observation. But what I said earlier, and another thing we can do is to further restrict these data into some operational category. For instance, typically in terms of managing crisis, the damage index 0 and 1 are going to correspond to building deemed as safe. The building with damage index 4 and 5 are going to be unsafe with no occupancy possible, and the 2 and 3 are going to be building labeled as with restricted access, for which one can enter the building but for a limited duration. So the challenge here is that, as you see here, all these data set comes from eclectic data set because they come from many different regions of the world with many different types of building. But here, if we want to make the case for a specific city, let's say San Francisco, how can we apply it with data set that might not have anything to do? So we can see from that data set that relationship exists, but the relationship in Algeria, Japan, Italy might be fairly different from the type of earthquake and also to the building types we can see in San Francisco. So for this, what we need is to use data or to learn in real time from the building that will be inspected as the result from inspection are going to come, okay? So that means we're going to need to learn from few data points. And to learn continuously from few data points, the best approach to do this is using a Bayesian approach to characterize our posterior PDF for the joint probability density of our parameters, okay? So we're gonna walk step by step. So first we're gonna say, given D, our data set, which is made of here frequency ratio that are in the range 0, 1, and DI damage index for a set of data, the goal is to learn the conditional PDF of X given D, okay? In terms of learning, this is what we will have to do. I have to learn what is going to be the conditional PDF of my frequency ratio for each of the possible damage index. So I'm going to learn a first conditional probability PDF for damage equals 0, a second one for this set, third, fourth, fifth, and sixth one. Okay, so this conditional PDF can be represented by the PDF for my covariate X, the frequency ratio, which is parameterized by a vector of parameters that is function of the damage index. So in our case, since X is bounded in the 0, 1 interval, we're going to model it using a beta distribution. Then this beta distribution, we're going to choose to parameterize it by its expected value and standard deviation, which again, both are going to be dependent on what's the specific damage index associated with the covariate we're trying to infer the PDF for. And at the end, what we're seeking here is that posterior, okay? What is the posterior PDF for the parameter theta? So the expected value and standard deviation, conditional on data, okay? All the observed data across the different building I've seen. And to do this, we have to formulate the likelihood of observing data given the parameters times the prior probability of parameters divided by my evidence, my normalization constant. And at the end, what we're going to be looking for is the posterior predictive. That posterior predictive, as we've seen before, this is the conditional PDF for my covariate X, here my frequency ratio, given D, my damage index, and given all the data I have observed. To obtain this posterior predictive, I need to integrate my joint distribution for my covariate conditional on parameters times my posterior for my parameter value that would have been inferred in the previous step. And then I need to integrate that joint over the parameter value theta. Okay, so first step is to do the probabilistic learning. We need to define what are the likelihood and the prior. Okay, we're looking for that posterior, the posterior PDF for the parameters. The parameters here are my expected value and standard deviation for all these, all the possible damage indexes given data. Okay, and here if we omit the evidence, the normalization constant, we can say this is proportional to the product of the likelihood, the prior probability of my data given my parameter value times my prior probability of these parameter values. Okay, first thing we're going to do, we're going to define what is our likelihood. So our likelihood, which is the prior probability of the data given the parameter value, is going to be the product of the likelihood over all my data. So here are going to be the data, I have data points such that my damage index equals to the current damage index I'm looking at. Okay, so here my likelihood of my covariate X, my frequency ratio given my parameters, is going to be dependent on which type of observation do I have. So that likelihood, if xi is a direct observation, is going to be directly the PDF for my covariate given its parameter value, in this case the beta, okay? But what if x is a censored observation? It's going to be the CDF of my beta distribution for the same parameters. Because keep in mind what we had here is we had some direct observations and we have the indirect one, the one indicated by an arrow, which are upper bound observations. So in this case, the upper bound observations need to be treated using the CDF, okay? Because they're censored observation, where the other ones can be treated as direct observation with respect to the likelihood. For the prior probability, I'm going to assume I have non-informative prior knowledge, except for the constraint that I know that the expected value for a damage index of 0 must be greater than the expected value for a damage index 1 up to the 5th damage index. What does it mean? Is that I expect the safer building to have higher expected value, and this expected value should drop down as the damage index increases, because I expect higher and higher level of damages, so higher and higher shifted in the ratio of natural frequencies. Okay, so if I take all of this into consideration and I use a Markov chain Monte Carlo sampling in order to infer my joint PDF for all the possible damage indexes, for all expected value and standard deviation parameters, what I'm going to obtain is something like this. If I look at the pairwise joint PDF, I'm going to have here the joint PDF for mu1 and sigma 1. Okay, so all the dots you see are my MCMC samples. I have drawn it along with empirical contour plot so that you can see the shape of the joint PDF. Okay, this represents the joint PDF for the expected value and standard deviation for the damage index d equal 1. Then we have the same thing for d equals 0. So you can see that by adding d equals 0, which means a lower amount of damage, okay, so it means practically new, the expected value shift to a higher value. This corresponds to what we had in our prior knowledge, because less damage building should have higher frequency ratio, but we have more spread in the distribution. This is for damage equal 2 and 3, 4, 5. And keep in mind that we have no actual observation in our database for damage index equal 5. Okay, so how come we could infer the posterior for damage equal 5? It's because of our constraint here that the expected value should be graded for 0 and for 1 up to 5. Okay, so that allows us to here infer also some knowledge for damage index d equal 5. Okay, so here what you can see is that we still have huge amount of variability in our inference because we don't have any actual observation. But it doesn't mean that you have no observation at all. We have observation from the constraint we have applied to our problem. Okay, so what we have here is the conditional PDF, or actually what we want to obtain, what we have here is this joint PDF, okay? And here I can only plot the pairwise joint, but this exploration for the MCMC sample is in a 12-dimensional space, which means I have one expected value, one variance for each of the 6 damage index. So I have a total of a joint estimation of Markov chain Monte Carlo in a 12-dimensional space. And this gives me here the description for my posterior knowledge for the parameters, okay? So what I want to obtain is the posterior predictive for not my parameter value, but for my frequency ratio x, okay? And to do this, what I need to do is to integrate here with respect to my parameter value, which are mu and sigma, my expected value and standard deviation. I need to integrate the joint, where the joint is the product of my conditional PDF for frequency ratio given its parameter times the posterior PDF for my parameter. This is what I obtained previously with my MCMC sampling given my data. Okay, and if we do that exercise, marginalizing like this and integrating to obtain a posterior predictive with Monte Carlo samples is trivial, okay? And the result would be what I presented here in those curves. So each one of these curves is one of those marginal conditional posterior predictive, okay? This is the posterior PDF for a frequency ratio X, which, keep in mind, 1 would be assigned with a building that has no frequency ratio, frequency ratio equal to 1, meaning undamaged, and very low frequency ratio are going to be associated with highly damaged building because the frequency drops significantly after the earthquake. So this is the conditional PDF of frequency ratio, given D, a class, a damage index, and given my data set of observed building for which I knew what was the frequency ratio and what was the damage index. So we can see that for D equals 0, the building with the highest frequency ratio, so that are going to be associated with the least amount of damage, we see here this is the marginal PDF. Then for D equal 1, D equal 2, 3, 4, and 5. And again, keep in mind, for D equal 5, we didn't observe any building that fall into that category. But still, we're not blind. Because of our constraint on the expected value, we can infer what could be its distribution given all the other observation and the constraint available. Okay, but now we need to do one more step, because what we've inferred so far is the conditional probability of X, where X are the frequency ratio, given D, the class, and D, which is my set of observed data points. Okay, so this is what we have here. This is what's represented in that figure. But what we really want is not this. Okay, we need to reverse the relationship. What we want is the posterior probability of a damage index given an observed frequency ratio. Okay, how do we reverse this relationship? Through conditional probability, through Bayes' rule. Okay, so if I want to obtain that posterior predictive probability for a damage index given a frequency ratio and given my data, I'm going to obtain this by taking the product of the conditional probability of damage frequency ratio X given its parameters times the probability of that damage index. I divide by my normalization constant times my posterior probability for my parameter value. So again, this integral for marginalizing my uncertainty on my posterior parameter value, since I obtained that posterior through MCMC sample, I can easily marginalize this uncertainty through my sampling, through averaging my samples, sorry. And the outcome of this marginalization is this plot here, okay? This plot relates the conditional probability of a damage index from 0 to 5, given X, my frequency ratio, okay? We can see here I have a frequency ratio close to 1, okay? So what I have here, the height of each region will describe the conditional probability of each of the classes. So in this case, for a frequency ratio of roughly 0.9, we can see that I have a dominant probability for damage index being 0, okay? Something close to 0.75. Then I have maybe a 20% probability for damage index 1, and the sum of the height of the other region is the probability of the other classes. And I can, for any observed on-site frequency ratio for a given building, quickly assess what is the probability of each of those classes, okay? So this is what was really estimated using empirical evidence, okay? But how can we do this in real time? We're gonna make a simulated example where we assess, okay, what would happen after an earthquake in San Francisco, for which we have 389 buildings that are 10-story or more, okay? This is San Francisco city center. All the green dots represent a 10-story building that we have in the city. And here, what I've built is I've built a synthetic database of what could be the frequency ratio given the damage index. And each of these points represent what would be the response of one of these buildings, okay?
But right now, I don't assume that I know the damage index. I'm only going to know the frequency ratio, and I'm going to try to infer what is the damage index. So to do this, I start with no knowledge. I forget about the data I've used before. I start the learning process all over again. As inspector, are going to tag the building as being in damage 0, 2, 1, 2, 3, 4, 5. Okay? So my prior knowledge is like this. Is only what we can see is the conditional probability of frequency ratio given data. This is only constrained by my prior knowledge on the expected value. Okay? Here what I chose to do is to regroup the classes into either the damage index 0, 1, which is safe, 2, 3, which is unsafe with restricted access, or 4, 5, which is plainly unsafe. And what we have here is the percentage of building for which we can do an inference about the safety states as a function of the number of inspections performed across the city. Okay, so here what we see, I inspect a first building. This one was unsafe. It was actually belonging to a damage index class D equal 4. So I update my posterior knowledge for D equal 4. Then I observe another building. This one was safe. Okay. That was belonging, my inspector tell me it's D equal 1. I update my posterior knowledge. Okay, and I keep updating. A second building, D equal 4. And D equal 2. And I keep going on like this until I have a sufficient amount of confidence to start making prognosis. Okay, when I hit 10 inspection, I start to use my conditional probability I have learned here to make prediction about which building should be safe, which one should be unsafe. So the building that were actually inspected are those with the solid line around them. Okay, now what I do is that after having seen 10 inspection, I can make a prediction for about 40% of the building in the city. So all the dots that are green are those that are classified as safe. All those that are in red are those classified as unsafe. And here, since I know the truth because it's a synthetic example, I can assess that I have made 0% false positive, so buildings that are deemed as unsafe when they're safe, and I have 3.9% false negative. Okay, and if I continue to observe data, I can keep updating my knowledge for my conditional PDF of frequency ratio given data class, and I can keep doing more and more prediction in my city. Okay, this is how we can use a classifier combined with a Bayesian learning in order to learn in real time as data comes in. If you want the detail about this procedure, you can go see the following paper where the details are given. Okay, so we cannot always afford to do that full analysis, that full Bayesian approach to characterize or posterior knowledge for the parameter. It might be sometimes too expensive because we have too much data, too many dimensions, and so on. So some classical approach that are used in practice are either, the first one is going to be naive Bayes. In the naive Bayes, what we're going to do is that when we want to build the conditional probability of covariate given a class, we're going to build this by assuming that this joint PDF is the marginal are independent for x1 and x2, okay? So they're always going to give elliptical contour with no dependency. So for instance, we're going to say that xi and xk are always independent, conditionally independent, given the data, okay? So in this case, for instance, I could have a first marginal for x1 that is beta, a second marginal for x2 that is normal, and I obtain the joint by simply taking the product of the marginal. We call it naive Bayes because this conditional independence assumption. So my joint PDF for a given class Y is modeled by the product of the marginal PDFs. Then we have what we call linear discriminant analysis, okay? So we're gonna model the joint PDF for each classes by normal distribution, okay? So what's gonna differ between one class and the other is only the expected vector, okay? Both distribution for the class are gonna be parameterized by the same covariance matrix. So the mean vectors are estimated independently for each class. However, the covariance is shared across all data, okay? And the other approach that is fairly common is called quadratic discriminative analysis. So in linear discriminative analysis, the covariance was the same for both classes. It's not the case with quadratic discriminative analysis. So each class has its own covariance matrix evaluated empirically from the data available, okay? And why linear or quadratic is because if we make the hypothesis of a same covariance matrix for both classes, the boundary that's going to separate a probability of 0.5 for both classes is going to be linear in this case. Whereas for quadratic discriminative analysis, the frontier, the boundary is going to separate a probability of 0.5 for either classes is going to be quadratic here. Okay, this is where the names come from. The boundary, the frontier between the higher probability for one class or the other is linear. In this case, it's quadratic. Okay, so as a summary for generative classifier, the bottom line formulation goes through Bayes' rule, where we're seeking this posterior, and we're obtaining this through the product of the likelihood of covariate given a class times the probability of the class, and we normalize this with a normalization constant through our evidence, okay? When we want to go quick, or when we have large amount of data, we're going to use an MLE or point estimation to obtain only the most likely value for the parameter theta. When we want to go with a full Bayesian estimation, what we're going to do is that we're going to characterize our posterior predictive, okay? So we're going to infer what is our posterior for the parameter value for either the prior or the likelihood, and we're going to marginalize this uncertainty on parameters by taking the integral of this relationship with respect to the parameter value, okay? These are the two ways to go. So what are the strength and limitation of such a generative approach? So first, in terms of strength, it's compatible with any types of observation, whether they are direct or censored observation. So this is a strength in the case where we have to deal with complex observation that can be upper or lower bound. It's intrinsically well suited for Bayesian inference, okay? It works well, so it's easy to play with everything you want to make a Bayesian inference for all the quantity you want. And one main strength here is that you can handle unbalanced class observation, okay? It means what? It means that you can learn or you can adjust the probability of the class if in the situation where you want to apply the classifier, the probabilities of the class is not the same thing as what you had in your data set. So this is a key strength here. In terms of limitation, it's fairly complex to set up, okay? In the same way where we have a strength where we can adapt this to kind of any kind of reality, you might need to define more things to use a generative classifier because everything is possible. So it's more set up for tailored complex model structures or complex data set that have limited scope, because defining such a generative classifier for a large data set for a complex problem becomes quickly complicated. So what you can do to go around this is to use the simpler structures such as naive Bayes, LDA, or QDA, but the problem is that in terms of performance, they're typically outperformed by the discriminative methods we're going to see next. Okay, in terms of discriminative approach, the first one we're going to see is logistic regression. Logistic regression is actually simply an extension of the linear regression we saw in the regression module, okay? So we're going to first see a revision of linear regression. How does it work? And how can we extend this regression method for a classification setup? Okay, then we're going to look at what are the limitations of such approach and what is the need to see some more advanced approaches. So a quick revision of regression. So in regression, what we have is covariates which are continuous, X, and system response, Y, that are also continuous. So we assume that the underlying reality here is a deterministic function, okay? And we have access to some imperfect observation of that reality, where each dot here represents one observation, which is the reality plus observation noise. So here, our data set that consists in all of those points are a set of tuples, a set of d tuples, which are a covariate value, so the x coordinate, and a y coordinate, the system response, where both x and y are real values. So, or at least continuous values. So our model here is we want to retrieve g of x, the underlying deterministic function, by modeling as a function, a parameterized function of the covariate. So here, the hypothesis we have is that g of x, my function, is equal to the reality, okay? There's an underlying true function that exists. And here, that true function doesn't vary. The only reason that we observe variability here is because y, or observation, are actually imperfect observation. They are the true underlying reality plus v and observation error, which is actually a Gaussian, which are sample or realization of a Gaussian distribution with zero mean and standard deviation sigma v, or variance sigma v squared. Okay, this is for regression setup. Now for classification, what we have is that our outputs are not continuous values anymore. They're classes, either +1 or -1, okay? So here my covariate x are still continuous, but my system response are either, in the case of binary classification, -1 or +1, okay? So how can we approach this? How can we extend our linear regression setup for this classification setup? We can do it by using a sigmoid function. Okay, that sigmoid function, what is it going to do? It's going to squash the output of our regression, which is in the continuous space, in the interval 0, 1. Okay, so b0 plus b1x it's just a linear function. Okay, linear function of x, my covariate. Okay, this is still expressed in the real space. Okay, but what we're going to do is that we're going to evaluate this real number into sigma, which is bounded between 0 and 1. Okay, so if I take b0 plus b1x being z, that sigmoid function can be 1 over 1 plus exponential of minus z. And this function looks like this, where what I have here is as a function of my z value, so b0 plus b1x, what is the output of that function is something between 0 and 1. Okay, so transferring my output for my linear function into that 0, 1 function is going to return a probability. Okay, so if we summarize the step of going from linear to logistic regression, what we're going to do is we start from the covariates x. Okay, these covariates belong to a real space in x dimension. Then what we're going to have is we're going to model what we call a latent function. Okay, latent function is going to be a function that is not directly observed. Okay, in this case, that latent function g of x, which is the same case as we had in linear regression, is going to be my model matrix x times b, my vector of parameters. So as it was the case in the case of regression, here the output of this linear function is also belonging to the real numbers. Now what we're going to do is that we're going to evaluate the output of that latent function into my sigmoid. Okay, 1 over 1 plus exponential of minus z, where z is that g of x. And this is going to squash that output result from my linear function into the range 0, 1. And this is what's going to be modeling the conditional probability of a class y given x, some covariate responses. Where keep in mind, my function sigma of z is 1 divided by 1 plus exponential of minus z. That looks like this function. Okay, so here we represent graphically the interaction between all these quantities. What I have here as x, my covariate, okay, between 0 and 100. What I have here in that red line is g of x, okay? What is my linear relationship between my linear latent function and my covariate responses, okay? Imagine that we know that function. What we're going to do is that we're going to pass it through the sigmoid, okay? What do I mean by pass it through? So for a given x equal 25, I read what's going to be the g, and for a given g, I will pass it through my sigmoid function. And if I go here, I follow the graph, this is going to be the height. This is going to represent the probability of the class y equal +1 given my covariate value x. Okay, this is how we do these 3 steps. So, but what we have to do here is actually the reverse way, because I don't actually observe g of x. The only thing I observe are these pink crosses, which represent some classes observation as a function of x, the covariate. And I need to infer from these class observation what are the optimal parameter of my linear function that's going to maximize my log likelihood, that's going to predict ahead what is the probability of each of those observations. So to do this, I first need to develop what's going to be the marginal likelihood. Okay, I have to split my data according to each class. Okay, so I start for all the xi's corresponding to the class y1 equal +1. Okay, in this case, it would be these 2 data points. Okay, what I'm going to do is that I'm going to build my function, so my model matrix, for all the data points that correspond, or all my xi for which yi equal +1. So in this example would be these 2 data points. Then I can say that my conditional probability of y equal +1 given x, this corresponds to my likelihood, is equal to my sigmoid, so my blue function here, my nonlinear transformation function, evaluated for my model prediction. So my model matrix times my model parameters. So this is equal to sigma of xi, in this case here, because I have a simple linear function. So now I have to do the same thing for the second class. So yi equal -1. Okay, I build again my model matrix for all the xi equal -1. And my conditional probability of y equal -1 given x is going to be 1 minus the sigmoid of x -1 times b. Okay, so I have, why is it this? Because if I want to obtain what is the probability of predicting these 2 points given x that is, for instance, low, the probability of predicting these points is not a low number, it's a high number. Okay, when I look at the opposite class, I need to do 1 minus the output from my classifier. Okay, so here we can see from this model that I have a high probability ahead of having these 2 points in that region. If I want to have the probability of these 2 points, I have to take 1 minus this model here. So the joint likelihood is going to be the product of the 2, okay? But if instead of looking at the joint likelihood, we look at the joint log likelihood, everything that was before product becomes sum, okay? So I'm going to make the sum of everything I had here for all my observation, the sum of what I had here for all my observation, and I sum both terms. This is going to be my joint log likelihood for the probability of predicting ahead my data given my parameter value. Okay, and what we're going to do here, treat that as a maximization problem. Okay, we're going to try to find the argument b, my parameter value, that are going to maximize this log likelihood. So the specificities here is that in linear regression context, we could directly infer analytically our Amelie parameter estimate. Why? Because if we would derive our log likelihood, that would be a linear function. So we could set that derivative, which is a linear function, equal to 0, and directly solve for our parameter b. But here, that function, because of the nonlinear sigmoid function, we cannot directly obtain that linear form. So since we cannot obtain the linear form for this derivative, we cannot directly maximize explicitly in closed form. So what we have to do here is use a gradient optimization algorithm, such as Newton-Raphson, such as gradient descent, okay, to find what are going to be the optimal parameter values. Okay, so if we put that into application, here I've generated synthetic data, okay? The synthetic data is that red dashed line here for the latent space and for this classifier, okay? And from this synthetic reality, I've generated samples, okay? So samples of observations. I have 1, 2, 3, 4, 5 observations, okay? And what I did is I used those 5 observations to retrieve what are going to be the optimal parameter value using a Newton-Raphson approach to find the best parameter that best explain the data. And these parameters are going to be the parameters of that red line here. So we see that it's not that bad, but we don't have an exact fit between the underlying synthetic truth and what I obtain using an MLE approach. Why? Because I don't have enough data. Okay, if instead of using 5 points, I use 1, 2, 3, 4, 5, 6, 7, 8, 9 points. So we see that we're getting closer to reality. If I use a bunch of points, maybe something around 100 here, we see that I can exactly retrieve the relationship. Okay, don't here get too excited. I can retrieve the exact thing just because here my underlying process, the real one, is linear. Okay. If the underlying process is more complex than the perfect shape of that sigmoid, I won't be able to have a perfect match between the truth and my classifier, okay? So this is a big limitation here. Here it works perfectly just because I'm in a trivial context. In much more complex cases where the true shape of that function is more complex than a sigmoid, is not gonna work as well. So the main limitation of this logistic regression is that just like for a linear regression, you need to unpick the correct transformation function for it to work well. So in 1D, it might work properly. When you deal with a large number of dimensions, unpicking these correct transformation becomes super, super difficult. So almost infeasible. So, and it's very difficult, as I said, when you have more than one dimension. If you want to do it, you have to do it through cross-validation to be sure that you're not going to do overfitting. Again, another limitation, there's no analytic formulation to estimate the parameter, contrarily to what we had with linear regression. So here, estimating the parameters might be cumbersome. And the formulation I've shown here is only compatible with error-free direct observation. We couldn't use upper bound observation or any kind of censored observation. It wouldn't be compatible with this formulation. So globally, this approach is good for understanding the concept of classification of discriminative classifier, but it's not going to be as powerful as either Gaussian process classification or the neural network methods we're going to see next. So when is it used then? It's used for a simple problem with low number of dimension, and it's used where in the cases where you want to interpret, you want to give a physical meaning to the model parameters you're looking at. So this is typically used in transportation models, in what we call discrete choice model, where we can associate the values of the parameters to some kind of economical interpretation or socio-economical interpretation of the parameter we're inferring. Okay, so now let's see in the methods that can really reach state-of-the-art performance in terms of classification. Okay, so what we're going to see now is an extension of the Gaussian process regression we saw when we were dealing with regression. Now it's called Gaussian process classification. And the extension of this approach is highly similar to what we saw with going from linear regression to logistic regression. Okay, this is highly similar. Now we're going to use as our regressor Gaussian process regression, and we're again going to pass it through a nonlinear function that is constraining the output of our GPR in the interval 0, 1. Okay, so we're going to compare GPR and GPC. Then we're going to see how can we update a Gaussian process using exact observation, and how can we modify these exact observation not for the regression context, but for the classification context. Then we're going to see how all of this can be used in existing package, such as GPML, Gaussian process for machine learning. Okay, so before going with Gaussian process classification, let's make a quick recap of what we saw before, the Gaussian process regression. Okay, so let's say that given a system response, so G of I is an observed system response. And here we're going to observe, we're going to assume we have access to exact system response observation. Okay, our reality is going to be G of Xi, is going to be this system response that depends on a vector of covariance. And here we assume, just like we did with linear regression, that the underlying reality is deterministic. Okay, it's function of the covariate Xi, but for a given Xi, there's always the same system response. And this thing is a real quantity. And here x is a vector of covariate, which is x-dimensional vector represented by that typeface x, meaning the number of covariate. Okay, so in terms of data, what I have a set of d tuples, xi and gi, where xi is a vector of x covariate, and gi is its associated system response. So here, what I have in my global data set is a set of d system response and a matrix of d times x. So I have d system response and I have x different covariates. So with my Gaussian process, what I want to do, I want to express my prior knowledge for what is the spatial dependency. When I say space, it means the space of my covariate. And how that this prior knowledge evolves as a function of the distance between my covariate, but only in the 1D space, could be in an n-dimensional space. Okay, and to do this, we need to define our prior knowledge for the expected value, the mean of our Gaussian process, and the covariance. Here, where the terms in that covariance are going to be controlled by our prior variance at any point I and j, and by a correlation function, where that correlation function is going to dictate what is the correlation coefficient between the response at two different covariates that are characterized by xi and xj. And the closer xi and xj are, the higher is the correlation. The farther apart these two covariates are, the lower the correlation becomes. Okay, so that correlation function is a function of the absolute value between xi and xj. So this is a look at my correlation function. As a function of distance between xi and xj, this is the correlation. So if the expected value here, the distance between my covariate is 0, correlation is going to be 1. This is a square exponential correlation function, and we can see that the correlation decrease as the distance between xi and xj increase. So in that example, my correlation length was L equal 1. The more I'm going to increase this, the slower is going to be my decrease in correlation. The less is going to be my correlation length, the sharper is going to be my decrease in correlation value as the covariate gets farther and farther apart. Okay, so as I say here, long go L equal 1, L equal 2, L equal 5, we can see that control the speed of decrease in my correlation as a function of the distance between my covariates. Okay, so we can see that the core principle behind GPR is that we can update our prior knowledge for the system response given the actual observation of the Gaussian process at some specific location. Okay, so given D, our set of covariates and associated system response, what we want to obtain is that posterior knowledge. Okay, we want to be able to predict at the system response at any location x stars, so any location that are either predicted or not predicted, and given the data that we've observed. And to do this, we need to represent our joint knowledge for G and G star. So remember, the star denotes the location where we want to predict. G represents the location where we have observation. So we need to represent our joint knowledge for location where we do have observation and those where we want to predict. Okay? And to do this, we need to define a mean vector. So a mean for the observed location for the prediction location, and a covariance matrix for both observed location, predicted location, and a cross covariance between predicted and observed location. And to do this, what we do is that we need to define each term in that matrix using these three functions. Okay, this is for the case where it's only the correlation function evaluated between observed location, the correlation function evaluated between prediction location, and the cross covariance term, where these two are just the transpose of the other, is a correlation function between observed and predicted location. So in that case, that posterior knowledge is going to be described by a normal, and this is going to be parameterized by this posterior mean vector and posterior covariance. And here the key strength is that in the Gaussian case, we can make the analytical inference for these two quantities. So for the mean vector and the covariance matrix, okay, where all the terms we have in here are actually have been defined here, and where J are our actual observation of the system response. So keep in mind here, we're still reviewing the context of Gaussian process regression. So here G is a quantity which is a real number, okay, between minus infinity and plus infinity. So how would it look like in practice is somehow like this. What we have on the horizontal axis as x, which is going to be the covariate value, and the vertical axis is going to be g of x, okay, or system response. So here the red cross represents the actual value where we have observed our process, okay? And what we have on the value x, where we want only to predict, is that we have uncertainty that increase. Okay, why? Because here we're far apart from the observed location. Okay, so we have more uncertainty regarding to what is the actual value that we can obtain here, to the opposite of where we have directly observed. The Gaussian process directly collapses to the observation. It collapses to the observation because here we assume that we have perfect observation of the system response. Okay, so this is the general behavior we would obtain with Gaussian process regression. Okay, how do we extend this to a classification context? To do this is very similar to what we did with logistic regression, which means we're gonna pass this Gaussian process into our sigmoid function. Okay, this is not going to be the same sigmoid as before. It's going to be a nonlinear function that's going to squash the real quantity output of our Gaussian process into the range 0, 1. And the output of this is going to be the function we see in yellow, which represent the conditional probability of y equal 1 given the values of x. Okay, this is going to be the discriminative classifier we're trying to obtain. But to do this, keep in mind, this here have uncertain value. This is a deterministic function. And in order to obtain that curve here, which doesn't have uncertainty, it means we need to marginalize the uncertainty associated with these values here. And so here, this function, this transformation function we see in red, is not going to be anymore the logistic function we saw before, 1 over 1 plus exponential of minus z. Why? Because here we need to be able to marginalize the uncertainty associated with our Gaussian process. And in order to do this, we can only do this for a specific transformation function. And in this case, we know that if we use as transformation the normal CDF, we're going to be able to do that marginalization analytically. Okay? What we're trying to obtain here in yellow is the conditional probability that y equal 1, given the prediction location and given the data available. And to obtain that posterior predictive, I need to integrate in order to marginalize my uncertainty on my prediction location. And in the case where my nonlinear function is a normal CDF, I can solve this integral analytically. Okay, it's simply the CDF evaluated by the expected value of my posterior here divided by the square root of 1 plus the variance of my posterior here. So here it goes well, but we have some steps missing. Okay, why? Because we did it in the reverse order. Okay, we assume that we had observation for our Gaussian process and we propagate this forward in the range 0, 1. But in practice, G is not observed. Okay, so we cannot directly make the update on the Gaussian process. What we're going to observe is not G, is actually classes, either +1 or -1. Okay, so here's our example of such classes. +1 or -1. So, and from these observed classes, we want to infer what could be the actual observed value for what is now a latent Gaussian process. So a Gaussian process that is indirectly observed only through my observation of the classes. So here from each observed value, so for each cross I have here, I need to infer what is GI. What should have been the observation for my latent Gaussian process. So that add one layer of complexity for the approach. Okay, so as you see here, for each of the 4 observations, I need to infer what is the uncertainty, what is the expected value for each of my observation location here. So this is what if we want to do it, this is how it looks like. So here I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 observations. And I have the 10 corresponding latent variable described by a mean vector and a standard deviation or a variance, describing what are the possible latent observations for my Gaussian process. And once I've inferred these 10 latent variable, which represent my virtual observation for that Gaussian process, I can use them to predict what should be the Gaussian process at any location. Then what do? I'm going to marginalize this uncertainty into that normal CDF, and I'm going to obtain what I have here in red, which is my conditional probability of the class y equal 1, given the covariate x and my data. So in this case, the underlying truth is that function you see here in dashed red. Here, if I have only 10 data points, my estimation is fairly poor. It's going to be that red line. But what we're going to see is that as I increase the number of data available, my estimated function is going to get closer and closer to the underlying truth. Okay? Before going there, we have to see a couple of things of how the mechanics of that latent variable inference work. Okay? Same thing as we saw before. The end goal we want to reach is this: obtain the conditional posterior for the class y equal 1, given the prediction location x star and my data set available. Okay? And this is given by the integral of the normal CDF. This is my transformation function. It's going to squash the output of my latent Gaussian process into the interval 0, 1. So this is conditional on G star, the output of my latent Gaussian process, times the posterior for my latent Gaussian process, okay? And that posterior depends on the data, but also on J, which are my latent observed value, okay? The observed values that are not available that I need to infer. And this we said that because of that special choice of nonlinear function, we could solve this integral analytically given by this value, where I have here the expected value of this posterior PDF and the variance of this posterior PDF. Okay, so that's the output that I have represent here correspond to actually here the confidence interval you see in pink. Okay, the expected value represent the dashed red lines. The pink values are the pink region is this marginal variance, and the G you see here is the actual green quantity here, which are the inferred latent observation at any location. Okay, so I need to obtain as a byproduct that conditional probability of my G star, predicting my latent Gaussian process at any prediction location, given G, my inferred latent variable. And we're going to assume that this is described by a Gaussian process. So this here is actually what we have in red here. And these quantities, the expected value and covariance, are given by these quantities. Okay? For the expected value, this, what it represents here is actually, so this thing here is the red dashed line here. It's function of mu star, so the prior knowledge for that latent Gaussian process at any predicted location, plus my cross covariance between predicted and observed location, my covariance at observed location, my prior mean at observed location, okay? And mu G given D is going to be the expected value for my latent observed value given the data. So here, if we assume that this and this is 0, oh no, not yet. We're going to come back to this later on. Now, if we define our covariance here, this is going to be a function of the covariance for predicted value, the cross covariance between observed and predicted value, the posterior covariance for my latent observed variable given the data, and my cross covariance between observed and predicted location. So in here, as I said, if we assume that we know these values, we assume that they are 0, this simplified to this formulation, okay? But we still miss something. We don't know what is the expected vector and the covariance matrix for the latent observed variable, those that are in green here. So this here is the green dots, the green crosses you can see here. And this here, if we look at the marginal, so the square root of the term on a diagonal of that matrix is what is represented by the the green lines you can see here, okay? But we don't have them, okay? I've plotted them on this graph, but I haven't tell you yet how do we obtain those. So to obtain those, we need to describe the posterior, okay? So these things are the parameters, the expected mean vector and covariance matrix of this posterior, okay? The posterior for the latent observation for my Gaussian process, which is going to be obtained as usual through Bayes' rule, okay? The likelihood of my data given the value of G times my probability of G given the covariate value divided by here my evidence, my normalization constant. If we say, okay, let's just assume we're working with unnormalized posterior, so we're going to drop the normalization constant. We're going to say this is proportional to the product of the likelihood of observing data given G times my prior knowledge of J given my covariate X, okay? And this again is described by, we assume it's described by a normal distribution, so a Gaussian process, and for which the parameters are what we're missing here. And same thing for the covariance. And what we're going to do is that we're going to approximate this posterior using what we've seen as the Laplace approximation. What does it mean? The expected value, we're going to find it by treating this as a maximization problem, okay? We're going to find what are the expected value that maximize my probability of predicting ahead the data. Then what I will find that the values mu g that maximize that log likelihood, I'm going to use the Laplace approximation to estimate that covariance by taking the inverse of the Gaussian of the negative log likelihood defined by this product, okay? So here we have the same quantity as we had before. So I need to first describe what is this, okay? The conditional probability of observing the data given the inferred observed value for my latent Gaussian process, okay? This conditional probability is going to be the product over all my data available of the conditional probability of a class, yi, given gi, my latent variable, okay? So my yi's are my pink crosses that you can see here. My gi are my values here for my latent inferred variable. Okay, and this conditional probability can be represented by the CDF, because this is that CDF I have here, of y high times g high. So here we restrict ourselves to the case of binary classification. So meaning that yi can either be +1 or -1. So in case where yi equal +1, this is just the CDF of gi, okay? CDF of gi. When the class is -1, we flip that probability by taking 1 minus the CDF, okay? 1 minus the CDF, because we're dealing with a symmetric normal CDF, is going to be equivalent to evaluating phi of minus j, okay? When y equal -1, it's going to be a -1 here because of the y high, okay? That's why we can model this conditional probability of the data given the inferred latent observation by this product over all observation of my normal CDF evaluated for the product of yi, which can be either +1 or -1, times gi, my latent observation. Okay, so what we do here is that we're going to infer our vector of expected value. So basically represent the green crosses you can see here, okay? The expected value for the latent infer observed variable, one of each corresponding to each of the cross we've observed. And we're going to solve this by doing a maximization problem, okay? By maximizing or finding the j that maximize the log likelihood we have here, okay? And to do this, what we're going to use is an approach similar to what we did with Newton-Raphson, which we're going to give us in a recursive setup that the new updated value for the expected value is going to be the covariance for my Gaussian process times at observed location times the gradient of my log likelihood, okay? And this is a recursive estimation. We're going to start with the initial value where all my infer variable, my latent inferred observation are going to be initialized at 0. Then I'm going to go through this process that takes into account the covariance for j, the gradient for my log likelihood, and I'm going to obtain new value for my expected value, okay? Then I'm going to replace them here and obtain new updated value, and I'm going to loop here until I converge to stationary value for my expected vector. When I would have completed that task, what I'm going to do is I'm going to perform the Laplace approximation, okay? I'm going to obtain the posterior covariance matrix by doing the difference between my prior knowledge for my Gaussian process minus the Asian of the negative log likelihood. Okay, the likelihood was defined. Here. So this is my likelihood. I'm going to take the log of it, the Asian, and I'm going to inverse all of this. This is going to be my prior knowledge for the covariance. Okay, so this mean vector represents the green crosses we have here. The covariance, if we look at the square root of the diagonal terms of what we have here, is the green line we have here. And then what we can do is use this in order to update our latent Gaussian process to predict at any location that wasn't observed. So right now, if we use only these quantities, we can only predict at these points. If we predict at all points, we have the continuous prediction for our entire domain. Okay, so here it might seem complex, but once it's implemented in the code, it's super easy to use. So for instance, the GPML package or PyGP that you can find in Python can directly deal with this. So in the context of GPML, how would you use this? So you start by defining what are the observed covariate, x obs, what are the observed system response, y obs, that are going to be classes, either +1 or -1. And you define a vector x spread of all the location where you want the GPC to predict what is the probability of the class y equal +1. For GPML, you need to provide initial guess for the correlation length, initial guess what is the prior knowledge for the standard deviation of your Gaussian process. You can initialize this at 1. And you define your hyperparameter knowledge. ep.cov, you take the log of your parameters of the 2 correlation length and initial standard deviation for your variance of your Gaussian process. We define that the prior mean is 0. Okay, ip.mean is 0. Then we're going to optimize these 2 parameter value using the minimization function in GPML. So here we say that take as many steps as you want to find the best value. And here our inference method is going to be the Laplace inference. Okay, the same thing as we've seen together previously. The mean value is constant with mean 0. We have a square exponential covariance function. And we use the error function as our likelihood. Okay, this is a normal CDF we've seen together. So this is going to update, is going to maximize the probability for our prior parameter. Then once we have this, we can directly use GP to predict the log of probability for the class y equal +1. Okay, in this case, you define your hyperparameters that was updated here. We still have the same inference method. We still have the main prior mean 0, the main covariance function. We have the likelihood function, which is here an error function, which is our normal CDF. We have our actual observed value for the covariate or observed class. Where do we want to predict? And the class we want to predict is the class +1. Okay, so that's why we have 1 here. We want to predict the log probability for the class +1. Okay, so if we take the exponential of what we have here, this is going to be directly the probability of y as I plotted earlier here. This is going to be directly plotting this thing here. Okay, so if we make an example out of this, I have here several observations for the class. The underlying truth is the dashed line here. And what we can see that for each of the observation, what's going on under GPC is that it's going to infer my knowledge for the latent observed variable associated with the Gaussian process. So the expected value is the center, and the length of the line represent the standard deviation associated with each of those observations. So we can see that we're not excellent, but we're already pretty good. What if we increase the amount of data? Okay, not really much better. Okay, if we use a lot of data, we're gonna see that we're getting closer and closer to the truth, okay? And contrarily to linear regression or to logistic regression, we didn't have to define any basis function, okay? If we feed enough data, it's gonna learn on its own what are the underlying relationship between X, the covariates, and the classes Y, okay? But here, keep in mind that data associated with a class is not as informative as data associated with the Gaussian process regression, okay? So we need a lot more observation about classes to make the same quality of assessment of our model than what we needed with the regression setup. So the strength of GPC, Gaussian process classification, is that it's simple to set up for any number of covariant X. So all the codes that are available, either GPML, PyGP, and there are many others, they're already building to work with any number of covariant X. It allows interpolating and extrapolating because it's going to provide uncertainty estimate with respect to the data to know, am I interpolating between two observed latent variable, or am I extrapolating outside the domain where I don't have any data available? The limitation is that it's only going to be compatible with error-free direct observation. So if you have censored data, you cannot use this. And when applicable, and you need to choose between regression and classification, you have to be careful about your choice. So last week we saw an example where we wanted to classify the volume of soil according, is it contaminated or not? And to do this, we were using a regression setup, where what we did is that what we were observing is not if the soil is contaminated or not. It is what is the contaminant concentration. And we use regression, so GPR, to build a model of the contaminant concentration across our volumes of soil. And from our knowledge of the contaminant concentration, we could deduce where am I contaminated, where am I not. Whereas we could have approached this problem differently. We could have said, we're going to build directly a classifier saying, am I contaminated or not? Okay? I'm going to directly use the observation of the lab telling me the concentration, the contaminant concentration, and use these values to train a GPC, Gaussian process classification, to tell me as a function of the spatial coordinate, am I contaminated or not? But the issue with this is that the classes observations are not as informative as the contaminant concentration observation. Why? Because when we have a class, you only know if it's contaminated or not contaminated. Okay, you don't know if you're far or close to the limit. Whereas when you build a regression model, you know you're modeling directly the contaminant concentration. So in addition of knowing if you're below or above the threshold, you also know if you're close or far from it. Okay, so generally, if you can choose, you're better to use or to create a regression model and use this to then make classes rather than directly working with a classification setup. Okay, this is not always possible. Whenever possible, you tend to have more observation or more information by working with real quantity in a regression setup than when working in a classification setup. But as I said, it's not always possible, not always convenient. You have to see what's available in your specific context. Okay, and the performance of Gaussian process classification in terms of computational performance is much less than Gaussian process regression. Okay, why? Because we have all these variables to infer using a recursive approach. Okay, all these latent observed values for our latent Gaussian process needs to be obtained through a recursive optimization approach. So this is computationally demanding, so it's going to be a lot more limiting when you have large data set. Okay, so when you have more than 100,000 observation, Gaussian process classification becomes really computationally demanding. So it might be one of its limitations. Okay, the last approach I want to see with you today is how can we use neural networks. Okay, neural networks are another class of discriminative classifier that can be used and that are extremely powerful and really well suited for large data sets. So we're going to look at an introduction where we're going to go back and look at what was the regression setup. Then we're going to see how can we define the structure for such a neural network and how does this is embedded into what is called the deep learning. Okay, so our setup is the same as we had before. Okay, our data set is made of tuples. Xi, which are continuous covariates, so can be defined in a real number, and Yi, which are class observations. So right now we're just going to limit ourselves to binary classification. So either Y equal -1 or +1. Okay, +1 for one class, -1 for the other class. And what we want to do is to use that neural network in order to build that discriminative classifier, okay? That's going to model the conditional probability of Y equal 1 given my observed covariate X, okay? And to do this is going to be very similar to what we did with logistic regression, okay? We're going to have a nonlinear function, which is going to take as input here a function. So in the case of logistic regression, what we did, our function was W0, origin for my linear function, plus W1 x1, W2 x2, W3 x3, in the case where we have X equals 3 covariates. And where sigma here is actually the logistic function, okay? So, and Z is what I have inside my parenthesis here. And again, just like with logistic regression, it looks like this. So what I've represented here is not yet a neural network. It's the same thing as logistic regression, okay? We have in this example, 3 covariate, x1, x2, x3. I have W0, which is the origin of my linear model, or my, in this case, 3-dimensional plane. I have W1 times x1 plus W2 times x3, x2 plus W3 times x3. And the output of this polynomial term is going to be squashed into the interval 0, 1 by this logistic function. Okay, 1 divided by 1 plus exponential of minus z. Okay, and this is going to be my observation Y of class, which can be either +1 or -1. Okay, so this is the context of not necessarily a neural net, but right now it's more of a logistic regression. How do we extend this in the context of a neural network? So instead of adding just one hidden unit here, I'm going to have a whole hidden layer. Okay, in my hidden layer, I can have many hidden units, which are all going to be obtained by the combination of W times X, W times X, W times X, and I then squash this into the activation function, which is going to be here, for instance, a logistic or a ReLU function. In this case, I do the same thing with different weights, but the same input covariance. And then I take the output of these activation function, I do W1 times the output of the activation function, plus W2 times the output of the activation function, and then I again squash this, but here specifically in the sigmoid activation function. That's going to quantify here what is the probability for Y equals, say, 1, the probability of my class. In practice, we don't have only one hidden layer. We can have an arbitrary number of hidden layers with an arbitrary number of hidden units. And the more hidden units per layer, the more powerful is or the more flexible, the more capacity has our model to learn complex relationships. But this will come to the expense to add the increase in the number of parameters we need to deal with. Okay? And when you hear the term deep learning, it refers to the depth of the hidden layers here, which can be in this simple case a simple fully connected neural net because all the hidden layers in 2 successive layers are fully connected, or it could be convolutional architectures for image recognitions and so on. Okay, but here deep learning is basically a neural net which is gonna have a deep structure, so many hidden layers. So we have here in terms of nomenclature X's, which are our input layers or covariates. We have our hidden layer and we have our output layer. And in the context of regression, our output layer was simply a linear function. In the case of classification, our output layer is going to be a logistic function. So in the case of binary classification, we can easily generalize this for multiple classes. Okay, I'm not going to go in multiple classes, but you can look at the reference, for instance, in the book, where we can we can easily generalize this to an arbitrary number of classes. So the main strength of using a neural network approach is that it really represents the state-of-the-art approach. So it's really what's beating all the other approach. And this is especially true when the data set is large and for a large number of covariates. So it really has unequal regression classification accuracy, but this is true when you have a large data set. Why? Because in order to perform the Gaussian process regression or Gaussian process classification, you need many activation units. Okay, you need many hidden units in your hidden layers. And when you have large number of hidden units, you're gonna have large number of parameters, sometimes millions, if not hundreds of millions of parameters. Learning millions of parameters means you need a lot of data. Okay, so in this case, it's going to perform extremely well when you're going to have large amount of data. Whereas with Gaussian process regression or classification, it tends to work a little bit better in the moderate data regime. Okay, so if we summarize what we've seen with the generative classifier, this is what offers the most flexibility. So for instance, if we have to model censored observation or indirect observation, we can do this. We can accommodate pretty much any situation. But this comes at the expense of we need to define a lot of things if we want to achieve a good classifier. So that's why it's best suited for small data sets that are mission critical, okay, where we really want to model all the little features we can have in our problem. And we can afford it because it's a small problem, okay? But for larger problem, if we want to apply the classic either naive Bayes or LDA or QDA, linear discriminant analysis, quadratic discriminant analysis, it's not going to perform up to the task of the discriminative classifier, such as Gaussian process classification or a neural net. So Gaussian process classification, once you understand what the mechanic behind it, everything's already implemented in the package. It works really well. It's quick and easy to set up your problem. It's going to allow to differentiate between interpolation and extrapolation because it provides uncertainty estimate on the latent Gaussian process that is there underlying the issue, underlying the problem. And it's best suited for medium-sized data set, but it's going to be more data hungry in a classification setup than in the regression setup we saw last week, just because you have a lot more things to infer. In this case, when I mean things, I mean these latent hidden observation, for which I need to infer the expected value and the covariance. So a lot more demanding to work in a classification setup than in a regression in terms of number of data. And then if you have lots of data with Gaussian process classification, it's not going to work well because it's going to become computationally really challenging. And it's going to become outperformed by techniques such as neural network, also often referred to as deep learning, which really owns the state-of-the-art, uncontested state-of-the-art method for large data set, complex data set, for a large number of covariates, large numbers of system response. This is what works best. However, to really be able to extract all that performance from your neural net, you typically need large data sets, okay? Often tens of thousands, if not millions of observations. Okay, so depending on what regime you're in, what are the specificities of your problem, you might choose what is best suited for you, either a generative classifier or a discriminative classifier such as GPC or neural network. The only case where I would see where it's really useful to use something like logistic regression is if for your specific purpose, you want to tie some interpretability to the parameters of your model, as it was going to be the case in discrete choice models that are extensively used in the fields such as transportation engineering. So that's all for the classifying methods that I wanted to see with you this week.